Okay, in this problem we have two different current carrying conductors. One's a single wire loop, the other one's a long solenoid. And these two things are situated so that the wire loop goes around the solenoid and the axis of the wire loop and the solenoid are aligned. Axes are aligned. And so the question is, if I'm flowing a certain amount of current through the wire loop, how much current do I have to flow through the solenoid in order to get a zero magnetic field at the center of the wire loop? Okay, so what are we going to do? Well, we're going to use some derived results in this particular problem. First, we're going to calculate the magnetic field on the axis of the wire loop. Now, in general, that's given by mu naught times the current through the loop over 2 times the radius squared, just going to write as a up top, over x squared, that's the distance from the center of the loop, plus a squared to the 3/2. Okay, so now at the center of the loop, we have the fact that x is equal to 0. So what does this mean? Well, that means that the magnetic field of the loop at its center is equal to mu naught I over 2a at its center. Oops, that's not how you spell center. Okay, like this. So that's the magnetic field due to the wire loop. What about the magnetic field due to the solenoid? Well, the magnetic field due to the solenoid is uniform in the center of the solenoid. We used Ampere's law to figure out what that was. We found out that was mu naught N times IS, where IS is the current through the solenoid. Mu naught's the constant, and the N is the number of turns per unit length. Okay, so in order to cancel out the field from the loop, we need to have the same magnetic field in the solenoid as we do in the loop. So what that implies is that mu naught N IS is equal to mu naught I sub L over 2a, where a is the radius of the loop. Okay, we can solve this for the solenoid current, and that winds up being I sub L over 2a N. Well, we're given the current of the loop. Look up here, we can see the current was 4.5 amps. So this is 4.5 amps all over 2 times the radius of the loop, which was given as 5 centimeters. We'll call it 0.05 meters. And then we need N, the number of turns per unit distance. Okay, I look up here. It's 15 turns per centimeter. Okay, so it says it's 15 turns per centimeter. I wrote the radius in meters. It means I have to write the turns per unit length in turns per meter. So that's 1,500 turns per meter. I can see the units work out in that case. Okay, so relatively simple expression. I can solve for this. I find that the solenoid current that is required is 0.030 amps, or 30 milliamps.